All right, well, happy Wednesday. Hope everybody's having a good day. We are in the home stretch here. We just have one little bit to still talk about. You know, we're looking at solving systems of equations, and we've been looking at the ones that um, have constant coefficients and are actually homogeneous. I didn't actually tell you the difference between homogeneous and non-homogeneous, so I'll hit that today just so you can see it. But we're only going to deal with homogeneous. But we saw that it came down to finding eigenvalues and eigenvectors in order to find solutions. And kind of the question that still is out there is what happens if we get like complex eigenvalues, because that happens. It's not all that uncommon. So that's what we're going to do. But before we could jump into that, any questions on any of the homework or other stuff that we've talked about so far that you'd like to address? 9 to number 29. I will put that on our list here, Victor. All right. Any others? Okie dokie. So let me go ahead and switch my screen here so you guys can see that. And then we'll go over it. All right. Let me zoom in a little bit. All right, so for number 29, it says find a fundamental set of solutions. And here we've got this d squared plus 6d plus 13 times d minus 2 squared times d cubed y equals 0. Okay, so looking at that, what the hell is the d? What does that even mean?
Derivative, maybe.
All right. When in doubt, we should always go back. Right, so they're using this as a shorthand. Right. Let me find where it first pops up here. Scroll back, scroll back, scroll back. Okay, so it says if k is a positive integer, let d of k stand for the kth derivative operator. So you're right, Bradley, it is a derivative, right? So when we multiply, when we've got dk times y, that's the kth derivative. Okay, so this is just their way of kind of making it a bit, well, less writing, basically. But let me go ahead and write this down so that we can switch to the whiteboard. So was it 29 you asked about, Victor? Yeah, 29. Okay, so we have d squared plus 6d plus 13 times d minus 2 squared times d cubed y. Okay, so let me switch to the whiteboard. So I think probably the biggest issue with this is just knowing what the heck they mean by that big D. But now that we've got it, let's see what we can do. So we have d squared plus 6d plus 13 times d minus 2 squared times d cubed y equals 0. Now, let me show you what this actually would look like if it was written as a differential equation. All right, so we're going to go ahead and FOIL this out. Times d cubed. Let's see, so that's d to the fourth. 6 minus 4 is 2d cubed. Squared 13 plus 4 is 17. Minus 24 is minus 7. The d's, we're going to get minus 52 plus 24 is minus 28. And then plus 52. And then that's all times d cubed. Okay, so I'm just doing the algebra here for you guys to see what this is going to look like. So this translates to 7th derivative plus 2 times the 6th derivative minus 7 times the 5th derivative minus 28 times the 4th derivative minus 52 times the 3rd derivative equals 0. So had it been written out the way that we normally would see it, it would have looked like this. Now, the fact that they wrote it out this way is actually really beneficial because think about what our step is. We start by creating the polynomial, which in this case would look like, oops, change to y's all of a sudden, r's, right? And so think about what our next step is. Our next step would be to factor this thing out. Oh, that should have been a plus. All right, well, if we factor it, we're going to get what they factored for us. It's going to be r squared plus 6r plus 13 times r minus 2 squared times r cubed. So I just changed all those d's to r's. So by them writing it in this form, they actually saved us all the algebra. All right, so now let's get our values for r. So obviously we're going to get r equals 0 from the r cubed, r equals 2 from this one. But now the r squared plus 6r plus 13, that doesn't factor. So that one we're going to have to do the complex stuff on it. Or not the complex, the quadratic formula stuff. So we get -6 plus or minus the square root of 36 minus 52 all over 2, which is -6 plus or minus 4i over 2. So that gives us r equals -3 plus or minus 2i. Okay, so we've got all of our roots. So now let's actually build our solution. So we're going to have from the -3 plus 2i, we're going to get e to the -3t times c1 cosine of 2t plus c2 sine of 2t. From the r equals 2, that's going to give me a e to the 2t, but then it's repeated. So that means I need a c4t e to the 2t. And then r equals 0, it gives me a constant, but it's repeated. So I'll multiply by t. And then it's repeated again. So I multiply by t yet again. So there's the general solution to this differential equation.
Okay, yeah, that makes sense. I just didn't understand what that D was.
Mm-hmm. Yeah, so they were just trying to help you out with the notation, right? By introducing this notation, they made it so the algebra was done for you, as opposed to writing it out like this and making you factor it yourself. So, all right, so good for that one?
Yeah.
All right. So any others? You'll notice that I didn't assign any chapter 10 homework just because we don't need more homework. You guys have plenty with the stuff from chapter 9. So Merry early Christmas or late New Year's or whatever you want to call it. Okay, so anything else? Or are we good? Homework stuff. All right. Well, then let's go ahead and hit the what happens when we have complex eigenvectors and eigenvalues.
I do have a quick question.
Yeah, go ahead, Bradley.
So why are systems of differential equations not always like y prime equals? We had an x prime in our example yesterday. I'm
So
just
we had
curious.
an x prime and a y prime.
Yeah.
So systems come about when you have multiple things whose rate of change is known. So you're going to have more than just the one derivative. You're going to have two quantities whose derivative is known. Because like you can't have, say, two that are y prime equals.
Because then they might. No, then it's
They
just saying they're the same thing.
they have to be the same thing.
Yeah.
Right. Because just think about, so y, that's our unknown. That's the thing that we're solving. And so you can't really have a system of equations with just one variable, right? Then it's just an equation, or I guess it is a system of equations, but it's a one variable system. But when we do systems in general, we have more variables, which in this case means we have more functions, which means we have more derivatives. So that's why always when we see systems of differential equations, they're going to have x prime, y prime, z prime, t prime, whatever, as many derivatives as we have unknown variables that are interplaying with each other. And obviously the size will affect how we get our solution or what the solutions look like, but it can be done in a similar process. Does that make sense?
Yes, it does.
Okay, cool. All right, any other questions? Okay, well then let me go ahead and go back to our whiteboard and let's start talking about the systems and all that. So what we saw is that every system of differential equations, we could actually write this as a matrix equation where we had some vector u prime was equal to a times u, where u was, say, xy. So u prime was x prime, y prime, right? And then the a just held all the information that we had from our system. Now, this one right here, this is a homogeneous. If we had a non-homogeneous, what it would look like, we would be able to write it as, again, a matrix equation. Oops, not plus. Sorry about that. So a prime equals, b prime equals au plus v. And as long as v is non-zero, this would be a non-homogeneous system of differential equations. And this actually kind of tracks. If you think about how we did it before, if I were to rewrite this, I could have u prime minus au equals 0. So all of our variable stuff is on one side and it equals 0. This one, we would get u prime minus au equals v. So all our variable stuff equals a non-zero vector. So we're actually using the same kind of definition as we did before. It's just now we're talking in terms of matrix equations. So we've been solving the homogeneous, and we saw that the trick here was to find the eigenvalues of A and the corresponding eigenvectors. And do you remember how we wrote our solution?
I mean, it's pretty much the same way as always.
Okay, but in this case, like, where do the eigenvalues and the eigenvectors go?
they were multiplied to our homogeneous solution. I mean, that's the way I think about it.
Well, we're finding our homogeneous solution. Okay, so here's where I'm going, is that our solution ends up being e to the RT times the vector, where if our eigenvalue, let's say, is lambda with a corresponding eigenvector v, let's say, then our solution u is going to equal e to the lambda t times v. So that was the whole point, was that we find the eigenvalues and their corresponding eigenvectors, because then we can build our solution set. Kind of ringing a bell, I hope, from a couple days ago. So let's do this. Let's do another example. Let's do one where we can go ahead and find these guys. I'm actually going to look one up from a DiffyQ book because I don't want to give us one that's got eigenvalues that are going to be an issue here. So how about we do this? Let's do a bigger system, one that's actually got 3, because there's no reason why we can't, right? We can extend these to be as big as we want. So let me just find one of those and we'll do it. All right, so here we go. Let's try this guy. So I'll change colors here. So for example, let's say we've got x prime equals y plus z, y prime equals x plus z, and z prime equals x plus y. All right, so there's an example of a system that now has 3 variables, but it's still linear and it's still first order, right? It's first order just because of the primes, and this stuff is all linear. So what we want to do is write this as a vector or matrix equation. So u, the vector u, is going to be x, y, z. That way we've got u prime here. So now let's build our matrix. There are no x's. There's 1 y and 1 z for the first row. 1 x, no y, 1 z, 1 x, 1 y, no z's here. So as a matrix equation, here it is. So what we're going to do, we're going to find the eigenvalues because when we kind of went through this derivation, we were looking for where the determinant was not 0, because those are the interesting non-trivial ones. And that led to eigenvalues. All right, so let's find the eigenvalues of this matrix. So we're going to do A minus lambda I. So it's going to be minus lambda 1, 1, 1 minus lambda 1, 1, 1 minus lambda. And now we need the determinant of that. So here's where we can play asteroids, or your favorite method of finding the determinant, but I'm just going to play asteroids. So I get minus lambda cubed plus 1 plus 1, so plus 2. And then I'm going to get minus a negative lambda, minus another negative lambda, and minus another negative lambda. So that's actually going to be plus 3 lambda. And we need to set that equal to 0. So let me just rewrite it with a positive, and we'll do it in descending order. So we need to find the roots of this. All right, now let me remind you just some of the tips for this. If you have technology, obviously you can just put it in something and say factor it. But look for divisors of this last one and check those. That's what we call the rational root theorem. So good choices to try are 1 and 2 and -1 and -2. So like, for example, if you plug in 2, you get 8 minus 6 minus 2, which equals 0. So I know lambda equals 2 is a factor or is a solution. So lambda minus 2 is a factor. And then I can build the remaining thing here. To get lambda cubed, I need lambda squared. This is minus 2 lambda squared. I need a plus 2 lambda squared, so plus 2 lambda. And then we're going to need a plus 1 at the end here. So there's the factoring for that, which then, now you can probably see the factoring here. So we get lambda minus 2 times lambda plus 1 squared. So we get lambda equals 2 and lambda equals minus 1. All right, so there are our eigenvalues. So now let's get our eigenvectors. All right, well, let me erase some stuff over here. So we got some space. All right, so let's start with lambda equals 2. So we're going to take that 2 and we're going to plug it back in here for the lambda. So a minus lambda I is going to look like minus 2, 1, 1, 1 minus 2, 1, 1, 1 minus 2. All right, so now we want to RREF it because what we're looking for is the null space of this matrix. Right? So what I'm going to do actually is just start like adding a bunch of these rows together so you can kind of see what ends up happening here. Now let's just go to RREF. So we're going to get, well, let's just start working on it. So we get 1, 1 minus 2. I'm going to move that guy to the top. Add 2 times this to this guy gives me a 0, 3 minus 3. Adding -1 to that gives me a 0 minus 3, 3. Those guys, of course, cancel. And then when I use that to reduce the top row, let's see what I get there. -1 plus 1. Should give me this. All right. So there it is in reduced row echelon form. Now I wanted to show you the 3x3 just to remind you this is a little bit more difficult than with the 2x2 where you can just swap the 2 values and then set it equal, and make one of them negative. Instead, look at what this first row is saying. This first row is saying x minus z equals 0. And the second row is saying y minus z equals 0. So x is equal to z and y is equal to z. So whatever I choose for z, my x and y are going to be the same. So an eigenvector for this guy, well, pick a z about 1, then x and y are the same. So there's the corresponding eigenvector to go with the eigenvalue of 2. All right, so there's that one. Now let's go to lambda equals -1. So if I put -1 in here for lambda, that gives me 1, 1, 1, 1, 1, 1, 1, 1, 1. And this one's really easy to RREF. And that brings us here.
And that's 2 rows of zeros because it was a repeated root.
So when you have eigenvalues that show up multiple times, you do end up getting a higher dimensional eigenspace. And that's what's happening here. Because if you look at this now, if we think about that equation, this is saying x plus y plus z equals 0. So x is equal to negative y minus z. And I actually have 2 choices here. I can pick y and I can pick z. So in essence, I'm going to get negative y minus z, y, z as my vector. And I can actually split this apart into the pieces with y and the pieces with z. I'm hoping that there's a little bit of familiarity there, that you kind of remember doing this when you did eigenvalues.
Yeah. And there's only one pivot.
Can you say that again, Victor? I'm sorry.
There's only one dependent variable, I think.
Yeah. So we
That
have
makes-
two free choices. Remember pivot columns and things like that. If I'm speaking a language you don't understand, just smile and nod, even though I don't see your pictures, just smile and nod. But basically, I now have 2 eigenvectors that correspond with the same eigenvalue. So this is our a repeated eigenvalue case. But here's what's kind of wild. When we go to actually create our solution, remember what we want is the e to the lambda t times our vector. Even though this lambda was used twice, I get 2 different vectors, which means I don't need to multiply by a t or anything like that because they're already linearly independent. So
that is pretty interesting.
Yeah, isn't that
how
kind
that
of
plays
cool?
out? Yeah.
That it just sort of worked out in this case, that there was no, oh no, we have to multiply by t. So here we go. Here's our solution then. We're going to put this all together. Here's how we're going to write our solution. So our vector u, it's going to equal, well, let's start with this one that was the 1, 1, 1. So I'm going to have a c1 times 1, 1, 1 times e to the 2t. So it was lambda 2, and my vector was 1, 1, 1. All right, then I'm going to get c2 times, pick one of these. So let's take that first one, minus 1, 1, 0 times e to the minus t. And then lastly, we're going to have c3 times minus 1, 0, 1 e to the minus t. If we wanted to separate it out as x, y, and z, which you might want, if we did that, we'd have x is equal to c1 e to the 2t minus c2 e to the minus t plus c3, oh, no, not plus, minus c3 e to the minus t. So I'm just reading across the top. Then the middle, y, that's going to equal c1 e to the 2t plus c2 e to the minus t, and then nothing from this guy. And then z is going to equal c1 e to the 2t plus c3 e to the minus t. So that's what these 3 functions would have to look like so that they satisfy the system down here. So it's kind of a neat little trick, a neat little way of doing this. But you'll notice that this took care of the repeated eigenvalue. It often takes care of itself by just creating those linearly independent vectors. But this also reminds you how to deal with ones that are a little bit bigger. When in doubt, just do this, rewrite the equations that the REF tells you. And then think about, what are my free choices? How many free choices are there? And that will help you get them.
And that was a 0 in the pivot columns. Correct?
The 0 in the pivot columns meant that, yeah, you have a free choice there.
Got it.
Yeah, so like with this lambda equals 2, the only pivot column that didn't have the leading one was this guy. And then in the lambda equals -1, you see the 2 of them are here. All right, so hopefully that's a good little kind of reminder of A, what we were doing last time, and B, how to deal with finding eigenvalues and eigenvectors. All right, so now let's talk about what happens when you get complex eigenvalues. So let me go ahead and clear all this stuff. Actually, before I clear, any questions before this goes away? Okay, so let me just clear all this. And let's talk about what happens when we get complex eigenvalues. Because they will show up from time to time. Okay, well, first of all, if you end up getting complex eigenvalues, they are going to be complex conjugates of each other. All right, so if you have, they're going to be, lambda plus or minus mu I. So let me just, oops, not lambda equals. We'll go ahead and call it R, just because we're used to having the lambda and the mu for our complex numbers. So we're going to get R equals lambda plus or minus mu I. All right. So we've got this fact, but I also want to point out that the U1 and U2, the two eigenvectors that we get, they are also complex conjugates. So that means that if, let's say, in our eigenvector, we've got a 1 plus I, the other one's going to have a 1 minus I. And this is what we're going to see when we get complex eigenvalues, the eigenvectors are going to be complex as well. All right, well, let's just go back to what we were doing to get our solutions, right? We saw that U was equal to, okay, well, there's going to be some constant, call it C1, times U1 e to the lambda plus mu I times t. And then we're going to get plus C2 U2 e to the lambda minus mu I times t. All right, so where we go from here is exactly where you think we're going to go from here. What did we do last time when we ran into this e to complex number stuff?
That's the sine and cosine, right? Or...
Yep, exactly. We're going to use Euler's formula to turn these into sine and cosine. So we're going to get u is equal to C1 times u1 times e to the lambda t times cosine of mu t plus I sine of mu t. And then we add to that the C2, U2, e to the lambda t times cosine mu t minus I sine of mu t. So just good old Euler's formula like we saw before. All right, now to kind of help us with this a little bit, I'm going to rewrite the u1 and the u2. Let's think about this vector u as a plus bi, where a and b are the vectors that hold the real parts and the imaginary coefficients, respectively. So then u2 is going to be a minus bi. So let's put these in down here to their respective spots. All right. So if we do that, and then we're going to just do a little bit of distribution kind of stuff, do some algebra, distribute it, all that good stuff. What this is going to turn into, it's going to look like sorry guys, my pen is acting up here. It's not letting me draw. There we go. Okay. So we're going to get u is equal to e to the lambda t. We'll just factor all that out. And we're going to get C1 times a cosine of mu t minus b sine of mu t. And then plus I times a sine of mu t plus b cosine of mu t. And that I should be multiplying all of that. So really all I did was I took everything that is C1 and I split it into the real parts and the imaginary parts. And then we can do the same thing with the C2. And this is when you go, okay, thanks for not actually showing us all the algebra and driving us insane with this. All right, I think I've got enough brackets for everything. Okay, so that's just separating it into the real parts and the imaginary parts. But notice how these things are very similar with the plus and the minus. And I don't know if you remember this, but back when we were dealing with complex powers and doing Euler's formula and all that back in the day, we were able to kind of play a little trick where you do a substitution on these. What you can actually do is take C1 and C2, and if you add them, call that, you know, 2 times your favorite other constant number. And then if you do C1 minus C2 times I, and call that your other, basically if we just combine these, what we can do, now these are going to be new C's, but this becomes e to the lambda t times C1 a cosine omega t minus b sine of omega t plus C2 a sine omega t plus b cosine of omega t. So like I said, these C1 and C2s are now different. C1 and C2s, they're actually related to the others. But anyway. So from Euler's formula and then a little bit of algebra, we get here. And this is what you want to box. Okay, put your box around this. And this is how we're going to form our solutions. Right? Because think about what we did was we go through this, we find eigenvalues, and we find out that they're complex. So they've got a real part and an imaginary part. So the real part of that vector is A, the imaginary part of that vector is B. So we're going to get that from the vectors. And then the eigenvalues themselves are going to give us the lambda and the mu. It's definitely uglier looking, but it should make total sense that now we're going to get sines and cosines. Because when we got complex roots before, which is the same kind of process that we're doing now, it led to sines and cosines as well. All right, so any questions on the derivation there, at least that you can think of as of right now?
Yeah, how do we find the a plus or minus bi?
Okay, so those are going to be from the eigenvector, and I think the best way to see how to do that is actually going and finding, we'll do a specific example that leads to complex eigenvalues, and I'll show you how we find the complex eigenvectors. It's actually done the same way that you find real eigenvectors, and then I'll show you how we can split it into the A and the B.
I just didn't realize that those were the corresponding eigenvectors. It makes sense now.
Yeah, that's what the U1 and U2, the way I have that written here, those are our eigenvectors. Okay, so these guys that are circled in pink are our eigenvectors. All right. I think I got enough space on the other side here. We'll just, I'm going to keep what's in the red box. I'll just eliminate a little bit more over here to give us some more space. All right, so let's try this with an example. And this is going to be our example. Let's say that we've got x prime equals minus 2x plus 6y. And then y prime equals minus 3x plus 4y. All right, so let's see if we can solve this. So we're going to start the same way. We're going to create our matrix A. So minus 2, 6, minus 3, 4. And then we want our A minus lambda I. So that's going to be minus 2 minus lambda, 6, minus 3, 4 minus lambda. So let's get the determinant of that. So we get minus 2 minus lambda times 4 minus lambda plus 18. If I distribute that out, I'm going to get y squared minus 2y plus 10. He says very unconfidently, but I think that's right. All right, so now let's find out what the lambda is going to equal if we want this to equal 0. So we're going to have r squared minus 2r plus 10 equals 0. So r equals 2 plus or minus the square root of 4 minus 40 all over 2, which is 2 plus or minus 6i over 2, or 1 plus or minus 3i. So there they are. There are our complex eigenvalues. So already in terms of our solution and what we have down here in the box, I already know lambda and mu. Lambda equals 1 and mu equals 3. So when we build this, we're going to get sine and cosine of 3t, and then we're going to get e to the 1t, right? Because the 1's going to go in for the lambda. All right, so now we got to find a and b. So what we're going to do is the same thing that we always do, which is plug in our lambda, or our eigenvalue, I should say. And I apologize that this is a different lambda, but we're going to plug in our eigenvalue into our a minus lambda I. So let's plug in the minus 1, or sorry, the 1 plus 3i. So we're going to get minus 2 minus 1 plus 3i, 6 minus 3, and then 4 minus 1 plus 3i. So that gives us negative 3 minus 3i, 6 minus 3, 3 minus 3i. All right, so now we're going to want to go ahead and RREF this like we've done before. So think about what you would do. I think it might be easiest if we made this top thing a 0. So if we're going to make that 1, 1 spot a 0, I'd have to multiply the bottom by negative 1 minus I. So let's just do that real quick. So I'm going to try to show you all the steps. So we get minus 3 minus 3i, 6. And then on the bottom here, I'm going to get now 3 plus 3i. And if I multiply this out, I'm going to get negative 3 plus 3i minus 3i plus 3i squared. So the 3i's cancel. The 3i squared becomes a minus 3 plus another minus 3 is minus 6. And now since those rows are equal, of course, they cancel each other out. I'm also going to divide out the 3's just because everything is multiple, a multiple of 3. So I'm going to get 1 plus I minus 2, 0, 0. So that's what this would look like if I got it down and reduced as far as I can. All right, so before I actually create my eigenvectors, any questions on getting down here? The good news is you're not going to have to do this by hand. You can, there are plenty of resources that just give you eigenvectors and eigenvalues of a matrix if you put the matrix in. I highly recommend that you use that so you don't have to do the algebra, but in a pinch, you can just do the algebra this way. All right, so remember the trick now with our two guys here. So our eigenvector, call it V, We swap these two and change the signs on one of them. So how about we just swap the sign on the -2? But this is going to be a vector that when we multiply by this matrix gives us 0. So exactly the same trick as before. But now we're going to split it into real parts and imaginary parts. So my real parts were 2 and 1. My imaginary were no i's and then 1 I. And so now, not only do I have the lambda and the mu for our formula, I also have the a and the b. A is 2, 1, and b is 0, 1. All right, so I now have all the pieces, everything that I need. So let's build the solutions to our differential equation. So clear some space up here. Be really careful. Leave what's inside the box, inside the box. All right, so here we go. We're going to get the solution is u equals e to the lambda t, so e to the t, times c1 times a, so 2, 1, times the cosine of 3t minus 0, 1, so that's my b, times the sine of 3t plus c2 times a, so 2, 1, times the sine of 3t plus 0, 1 times the cosine of 3t. And again, I want to go ahead and write them out separately so you can see what these things look like. So x is going to equal 2c1 e to the t cosine of 3t minus none of these plus 2c2 e to the t sine of 3t plus nothing else. So that's what x equals. And then y is going to equal c1 e to the t cosine of 3t minus c1 e to the t sine of 3t plus c2 e to the t sine of 3t plus c2 e to the t cosine of 3t. And so those are solutions to that original system of differential equations.
Why does x only have the first piece? Like,
Because of these zeros. The x gets all the top entries in the matrix. So it would have had a 0 c1 sine of 3t, which is why that's not there. And a 0 c2 cosine of 3t bit. So it was only because of that 0 that it went away. And if you go further to the, well, why did those zeros show up? Well, that was the nature of the matrix that was formed from the original system. Whew. All right, so these are two different ways of representing the solution, right? You can actually write it out as what the individual functions are, or, and this is totally acceptable, or be lazy and just write it as the one that has matrix, vector stuff in it. All right, so both of those are perfectly acceptable. And to a mathematician, you'll see us represent it as the first one just because it's easier. All right, so complex eigenvalues lead to complex eigenvectors, which lead to a much more complicated solution. But that solution just comes from the fact that it's complex. It leads to sines and cosines, because that's what happens with Euler's formula. All right, so how do you feel about that one? Yeah. I don't really feel like doing another example because the next example is just going to feel a lot like this one. But just realize that this is what can happen. Now, another thing that can happen, and I don't think I can just create a matrix that'll do this, but there are going to be systems that lead to having both real and complex eigenvalues, right? So you can imagine that once we are solving our characteristic polynomial, that we get maybe plus or minus I and 4 or something like that. So what do you think you do in that case? What do you think you do if you have both complex and real?
You combine the both.
Yeah, you would take this thing that came from your complex and then add to that the form that we get from our real. All right, so it's very much like when we were solving those higher orders, and sometimes you got complex and sometimes you got real and sometimes they were repeated and blah, 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 blah. Well, you took care of each case individually and then slapped them all together. And that's exactly what you would do here. So think about that situation where you had the two complex and one real. Your two complex would lead to a solution like this that has two unknowns, the C1 and the C2. And then you're going to get another unknown from the real one. You'll get a C3 times that e to the lambda t, whatever lambda ends up being. So if they get bigger and more complicated, so what? I mean, yeah, it's going to be harder to find the eigenvectors as you get larger dimension. But once you get the eigenvalues and the eigenvectors, you just put them together, just like we did any other time. All right, so questions on this one? Hopefully it kind of makes sense. And I would say that the most difficult part is this over here. Oops, that was weird. This stuff over here, that finding the eigenvectors given the eigenvalues, but just do the same thing that you did before, plug them back in, but then do a little bit of algebra with the complex. Whew. All right, so there was your real quick introduction to systems of differential equations. Now, we are looking at only homogeneous. And we're looking at only those that have constant coefficients. And obviously, as you make it bigger and more complicated, there's a corresponding complication to the process, but it starts the same. And in fact, if it was non-homogeneous, you're going to find a solution to the homogeneous and then add a particular solution. And so the goal is going to be find a solution to the particular. Well, obviously the method we used to find the homogeneous was similar to before. Well, so it's going to be the method we use to find the particular, but we're going to save that for a later class. So if you take more differential equations, you'll see that. Or if you run into it in one of your later science classes, you'll pick it up then. Anyway, all right, so I'm done. I'm done with new stuff. And if you kind of look at the clock and the calendar, you realize that we still have Friday and we have the rest of today. So I don't think I want to have class on Friday. I don't really see much of a reason for that. Seeing, I think the majority of you are not going to be taking the final. So let's just talk a little bit about that. I know that there's still some grades that are not input, some homework grades. I will get all of that stuff in by Friday. Okay, so by Friday, you'll have all the grades to everything you've done. It'll all be in there so you'll know where you're standing going into the final. I know that the final is optional for most of you. Remember, it's optional if you've done all of the homework with a score of at least 50%. And so for most of you, it's going to be optional. I want you to look at your scores, see if you want to take it or not, and then let me know. I would prefer that you let me know by Monday, because if it turns out that like nobody needs to take it, then I don't want to have to write one and get it all set up. But anyway, but the same deal as always, if you take the final, your grade can go up, but it can also go down. So keep that in mind as well. Also realize that if you're not pretty close to the next grade up, it's awfully hard to go change your grade that much with a final exam. You know what I mean? Like if you got an 85, no point taking the test because the final exam is not going to raise you to a 90, right? If you got an 89, yeah, then it might be worth taking the final exam, right? If you've got an 81, you probably don't want to take the final exam because you're not going to be able to raise your grade to an A, and there's the chance that you're going to slide back down. Okay, so just keep that in mind when you're making your decision. But like I said, I'll have all those grades up for sure by Friday so that you can make an educated choice in terms of taking the final exam. All right, and then I know, Jacob, you asked about having a review session for the final, and I'm definitely open to doing that, but I think I would rather do it next week. So let me look at my schedule, but I think we can probably pull it off at the usual class time on Monday. And I think our final is scheduled for Wednesday. Let me just double check that here real quick, unless anybody knows offhand when that was.
Yeah, I think it was scheduled for the 23rd, so next Wednesday.
Okay.
That is.
So so if it is that Wednesday, I just pulled it up. Yep, it is that Wednesday. So it's Wednesday, starting at noon, uploaded by 3 Pacific time. So that way, if we do a review on Monday, that still gives you a couple of days, and you can really, it also gives you time to study ahead of time and come with specific questions. So why don't we tentatively plan that we'll have a review session for the final on Monday of finals week. Again, I'll put this into the Canvas shell just to remind everybody. But that way, if you are going to take the final, you know that you can pop in and find me then. So think of it like an office hour, but a very directed office hour where we're going to work together to get whoever's there ready for the final. All right, so other questions? Anything else we want to talk about the class here for the next little bit? All right, so it's not sounding like there are any. So I'm going to go ahead and stop the recording. But before I do that, I just want to tell you all that it's been real. It's been fun. It's been real fun. I know this isn't how you wanted your LTCC career to end with all this Zoom stuff, but hey, we made it. You guys got through it, and you're heading to bigger and better things. So congratulations on making it. Good luck wherever you're going. Make sure you check back in with us. We love hearing from you guys, hear about your successes and everything. So with that, I'm going to wish you well.